Okay, so in this problem, we're first going to find the volume of a sphere using spherical or cylindrical coordinates, rather. So you draw just a circle and then kind of the equator. Whoops. And you've got yourself a decent picture of the sphere. Now, I'm going to say that the center of this sphere is the origin, and it has radius a. So what's the equation of this sphere? Okay, x squared plus y squared plus z squared equals a squared. Now, what's the value of the integrand? So the sphere is Q. What do we plug in for the, we'll call for right now the differential dv. What's the integrand? Okay, anytime you want to find the volume and you're using a triple integral, no matter what coordinate system you're in, what's the integrand? 1, right? So that's important to realize. So if we're using cylindrical coordinates then, and not spherical, but cylindrical, then what's dv? There's got to be an extra, think polar coordinates. There's got to be an extra factor of r, right? And then there's got to be another differential dz before the dr usually, dr d theta, right? So that would be the correct dv for part A, wouldn't it? Now, think of the floor, think of the ceiling to get the limits of integration on z. So the floor might be here, the ceiling might be here, except, well, we can make life easier on ourselves in a second, but let's just set up the full integral and then we'll use some symmetry to make it a little bit easier. So what value of z gives you the floor? I'll just solve this for z, right? Don't you get z squared, or z equals the square root of a squared minus the quantity. Let's do it as a quantity. X squared, is that showing up? Yeah, kind of. X squared plus y squared. And then we could put in a plus or minus. That'll give us both the floor and the ceiling. Do you buy that? Notice what I did. I subtracted x squared plus y squared as a quantity. Why did I do that? What am I going to replace it with?
R squared.
Yeah. Or how would the pirate say it? R squared, yeah. Okay, so what's the floor going to be for the inner limit of integration? That's the floor, right? So that's going to be the negative square root of a squared minus r squared. And the ceiling is the positive. Does that make sense to you? Now, if you project the sphere into the xy plane, what kind of object do you get? Circle of radius A. So that's maybe the worst circle I've ever drawn, but circle of radius A, right? So what does R run from for the middle limits of integration? 0 to A. And then it's really the entire sphere you project down, right? So it's really the disk that you're integrating over for the outer two integrals. And so to carve out that entire disk, theta goes from 0 to 2 pi. Now, to make your life a little bit easier, what could you do to make this bottom limit inner limit 0? In other words, make the floor some point in the xy plane inside that circle, right? So you can multiply the whole thing by 2. And okay, then this inner limit, if you do that multiplication by 2, this inner limit, lower limit becomes 0, doesn't it? Don't do that unless you're sure about the symmetry. Because some students think there's symmetry when there's not. You got to be really careful about that. Let's evaluate the inner integral. If we do that, we integrate, what do we get? So we get, okay, I'm going to leave r on the outside, and then we get z, right? Evaluated from 0 to that root, right? And then we still have dr d theta on the outside. All right, so we get 2 times integral 0 to 2 pi, integral 0 to a, and then we have r times that root, don't we? And then dr d theta. Does everybody buy that? And then this is my own personal preference. Since I just have a function of r in the integrand, my double integral that I've created here, and the limits of integration are constant, I can split up this double integral into a product of 2 single integrals, can't I? So this is just my preference, but I think it's easier on the eyes to split this up. Integral 2 times integral 0 to 2 pi. There is no function of theta, so just 1 d theta or just d theta, right? Then the integral from 0 to a of r times square root of a squared minus r squared dr. So what's the first integral? 0 to 2 pi d theta? It's just 2 pi times that 2 on the outside. 4 pi. Then this guy, what do I use on this guy? U sub. What would my u be? That's u, so what would du be? Negative 2r dr. Does that make sense? Okay. So what do I need to make a perfect du? I need a negative 2, so that means I need to multiply by negative 1/2. I'll do that out in front. I'm not going to evaluate the integral yet. I'm going to rewrite it. 0 to a, okay. I'm going to put the root in front just so you can really see what's going on. And then the negative 2r dr, that actually is my du. And I just wanted to write it over there so you can really see it. So this is like the square root of u right here, isn't it? Square root of u, integral square root of u du. Or u to the 1/2 du, right? So if you evaluate that, but don't actually make the substitution, what do we have here? So far we have bad news, negative 2 pi. We hope it becomes positive, right? Because we're looking for a volume. We integrate u to the 1/2, where u is a squared minus r squared. What do we get? A squared minus r squared to the, well, yeah, to the 2/3, well, 3/2, and then out in front, you multiply by the 2/3, right? And then we have that evaluate. Notice I'm putting the evaluation brackets. I'm leaving the constants outside the evaluation brackets. Make your life easy when you're allowed to. When are you allowed to do that? When that constant's a factor, right? Yeah. Evaluated from 0 to a, right? Okay, and then what does that make? Negative 4 pi thirds in front. Okay, you plug in a, you get 0, don't you? If you plug in a right there, you get a squared minus a squared to the 3/2, but that's still 0, isn't it? Subtract off now, what do you get when you plug in 0 for r? You're plugging in 0. Right, it's a cubed, right? Yeah. Minus, right? Does everybody see that? Everybody with me? So isn't that good news? Because then you do get positive 4 pi a cubed. Let's call it 4/3 pi a cubed. Which, of course, you can look up if you don't remember. That's the volume of a sphere of radius a. 4/3 pi r cubed is what we usually use, but we didn't want to use r because you wouldn't want to confuse that with the r from cylindrical coordinates. Make sense? Now, the second part, it's actually easier in spherical coordinates, which shouldn't be a surprise because you're finding the volume of a sphere in spherical coordinates, right? So do you want to try that one on your own? Do you want to see me set it up? What do you want? So set it up? All right. I will set it up for you, but the evaluation you won't need you won't need me to do. It'll be easy enough. Okay, so for part B, we'll just start part B here. We want to find the volume of a sphere. We're again going to use x squared plus y squared plus z squared equals a squared. So it's a sphere centered at 0, 0, 0 of radius a once again. I suppose I could use my picture from before, or just I guess I'll just refer to it. Okay, so think about an integral in spherical coordinates then. The integrand is 1, unless you consider that part of dv part of the integrand, which it does become part of the integrand. But the integrand normally, without any context, if you're trying to find volume, if you write it in the form of a triple integral, it's just the integrand is just 1. But in spherical coordinates, what does dv turn out to be? Yeah. So rho squared sine phi. Usually I do d rho, d phi, d theta. And then, so you have to think in space radially, right? And then the two angles, theta and phi. And let me go up to my picture up here. So think about what rho would have to range between. So just draw in a radius, right? A line segment from the origin out to the surface. What would rho range from? 0 to a, right? Because it's a sphere of radius a. So the inner limits of integration must go from 0 to a, because we're integrating first with respect to rho. Does that make sense? Okay, now phi, oops, too far. I want to remind you that if I put in some axes, the z-axis would be going up like this, right? And phi is actually the initial side of phi, the angle phi, is the positive z-axis, isn't it? And so think of a line segment. So think of this as the terminal side of phi, and the green positive z-axis as the initial side. How far would I have to go so that I'm carving out as much as I can of that sphere? I can't go beyond here, right? I can't go beyond pi for phi. So what does phi range from? From 0 to, actually that's pi, the straight angle pi. If you look at this angle here, that's pi, right? So we'd go from 0 to pi for phi. And then what would theta have to range from? Again, you could project it down into the xy plane if you like. Theta is going to range, well, it's going to be the same as before, right? 0 to 2 pi. Now, why is this so pretty? Yeah, it is better. It is easier on the eyes a little bit. But I want to point out you can split this up into a product of 3 single integrals right away, because the limits of integration are all constant, and you can separate the functions in the integrand, the function of rho from the function of phi. And it makes it a lot easier on the eyes. So I lied to you. I am going to evaluate this one, because if I don't, you guys might not appreciate how much easier it is if I don't show you right now. You appreciate it? Good. Okay, so when you write this as a product of 3 separate single integrals, you get 0 to 2 pi. Okay, that's going to be the outer variable of integration. So I don't see a function of theta, do you? So just 0 to 2 pi d theta. Okay, what's the integral with limits 0 to pi going to look like? Sine of phi d phi. And then 0 to a, rho squared d rho. Now we know the answer, right? We know it should be 4/3 pi times the radius cubed. So let's just verify. 2 pi for the first integral. Does everybody believe that? The second integral is going to be, what's the integral of the sine? negative cosine evaluated from 0 to pi. And we might as well do this one too. 1/3 rho cubed evaluated from 0 to a. You can see the a cubed popping out of that, right? So then 2 pi. Okay, what's the cosine of pi? So plug in the pi, get opposite of negative 1, 1. Plug in, okay, then minus, plug in 0, what do you get? You get 1, so minus 1, right, by fundamental theorem. So 1 minus negative 1, that is, because there's a negative built in. So you get 2 when the smoke settles. And then this guy is just 1/3 a cubed, right? So this is 2. So 2 times 2 is 4 pi a cubed. And then I'll put the 3 underneath the 4 because that's traditionally how it's written.